Thanks for the introduction. All right, so low back pain is the most common musculoskeletal condition affecting 80% of the population at some point in their lifetime. Intervertebral disc pathologies account for more than 40% of these cases. And damage to the disc, such as annular tears or bulges and herniation, may lead to nerve impingement and further pain. And current repair strategies, such as surgery or intradiscal injections, are invasive and they have not shown long-term clinical efficacy. So our group is exploring the use of pulse-focused ultrasound, or LIPUS, for extracorporeal treatment for low back pain and disc damage. LIPUS is an external mechanical stimulus that has been shown to be biologically active in several different cell types and has been used in multiple musculoskeletal applications, notably bone fracture healing, for which it is FDA approved for. And recent in vitro work in disc cells has been shown to elicit a matrix synthesis and response in both of the major cell types in the intervertebral disc. So for targeting and the repair of this disc tissue, it will require a uniform far-field energy targeted to the disc. And this talk is going to focus on our attempts to recreate that in an in vitro model. But we have also applied LIPUS in an in vivo model of rat tail disc injury, which we presented here in 2016. And we're also performing anatomical simulations to determine our sonication patterns necessary for reaching damaged disc. So let's talk about typical in vitro systems. So typically these systems put plastic cell culture plates on top of a planar transducer. And these types of setups are vulnerable to confounding factors such as standing waves, shear wave patterns, and absorption within the well plate. And this can lead to non-uniform exposure throughout your cell sample, as well as uncontrolled temperature elevations. And so for our application, it's critical for us to mimic the far-field sonication patterns that would be necessary for targeting deep tissues, such as the disc, while mitigating these factors that I mentioned here. And so our design concept will include planar transducers directed at a target placed in the far field, and our cellular target will be constrained by an alginate ring to remove the effects of well wall reflections and heating, and then the plate is topped by an acoustic absorber to eliminate standing wave formation. So we started off with some acoustic field simulations so that we could optimize our setup such that the full width at half max intensity covers our target exposure area. So we did this for various different frequencies that would be relevant for our application, and we saw that if we adjusted the transducer diameter and the offset distance, that we could get a broad exposure that is past the focal point within the diverging far field. This is some example data of looking at these parameters. And here is a visual demonstration of that. So we filled a well with some thermochromic material and exposed within the far field. And then we continued with some looking at characterizing the energy distribution at the cell position by performing hydrophone measurements. And so you see that if there's no plate within the beam path in the near field, there's this characteristic heterogeneity, and as you move off into the far field, it's more uniform. But if you place a 24 well plate with a narrow well in the beam's path, you'll see that the spikes in intensity are substantially increased. But if you place a well that is more wide, like a 6 well plate in the path, the beam profile is more uniform, and we can increase this uniformity across the sample by including that alginate ring that I mentioned before. And to quantify these differences in energy distribution, we use the gradient analysis method. So what you do is you calculate the slope between each point in the beam plot, and we're able to see that the mean gradient is reduced by 93% when you compare our setup to some of the typical setups that use a 24 well plate in the near field. So for our absorber design, we used a silicone absorber made of Silgard 170, which is highly attenuative and minimally reflective. And this sterilizable absorber is directly coupled with our cell culture media, and it has a baffled apical surface to scatter any reflected energy away from the cells. And we also performed some thermometry analysis by using thermocouples embedded in our absorber, a bead in the cell bottom, and we saw that there was negligible heating within our sample as well as the well bottom where the cells are in contact. And finally, we performed a biological validation experiment where we treated cells with either ultrasound or BMP7, a known anabolic growth factor. We treated for 8 days and then performed a hydroxyproline assay for total collagen. Collagen is an important protein that these cells must secrete in order to repair a damaged disc. And we saw a 2.6-fold increase in collagen production in cells that were treated with LIPUS. And interestingly, this effect size was very similar to that of growth factor treatment, suggesting that LIPUS may be a safer alternative. And so, in summary, we introduced an ultrasound exposure system specific to delivering uniform far-field energy in vitro while reducing the confounding factors that I mentioned. And we identified intensity gradient as a quantitative metric for comparing acoustic field distributions. We validated a platform to continue investigation of various LIPUS exposure parameters, and now we can move forward to dose optimization, including lower frequencies required to reach deep tissues. And so I'd like to acknowledge my collaborators as well as our funding sources, and thank you all for listening.
Very nice paper, thank you. What are your thoughts for ultimately applying this in clinical situations? How are you going to penetrate the bone to get to the disc? The bone's going to absorb most of the energy. Right,
so I think the idea is to avoid the bone. So as I mentioned early on, is that we're doing some modeling to see if there are any approaches that we can take to avoid any bone.
Yeah, okay, thank you.
You mentioned the exposure was for 8 days.
Yeah.
This was like a few minutes per day.
So it was 20 minutes per day, and we're also playing around with different amounts of days and treatment times as well, like the dose optimization that I mentioned.
Thank you.
Thanks.
So we made a record. We finished 4 minutes ahead of time. Thank you. And